An elastic rope for a bungee jumper says natural length of 10 meters and elastic constant K. When a woman of mass 80 kilograms is attached, the rope is stretched to a length of 11 meters. Find the value of K. Okay, so I'm going to represent the woman as a particle. The particle is 80G. Will somebody be so kind as to do 80 times 9.8 for me? 784. So she's 784 newtons is her weight, and her mass is 80 kilograms. Now, in this situation, because she's no longer, she's not going down and she's not going up, the tension in the string is equal to 784 newtons. This means K times your extension value must equal 784 newtons. What is our extension? It went from 10 meters to 11. So that means K times 1 is 784. This implies that K is 784 newtons per meter. Remember, K value is for every meter you extend it, how much force does it take? Is that right? So, now, the woman is now dangling 1.25 meters above the ground. An assistant pulls her down onto ground level and holds her there. Find the work done in pulling her down to ground level. Okay, so once again, we're representing this by, suppose we might need to make an assumption here. I think the assumption is that we're not really taking the ground into consideration. We're just taking the drop into consideration. Does that make sense? So the particle was here, and now it's located here. What's its total extension now? And her weight is still 784 newtons. What's going to happen when they release her? She goes up, because up will be bigger than down. Okay, so we're going to have to find the work done here. Okay, is the issue. So the work done will be the following formula. We were already 1 meter extended, correct? How many meters are we extended in the end? An extra 1.25, which is 2.25 in total. Our force is K times X, which is 784X. So therefore, the work done is by differentiating this. We're going to get X squared. We're going to divide by the new power. What's the new power? 2. So it's going to be 392X squared. We're going to integrate that from 2.25 to 1. I'll get the answer now in a second. And when you do that, you get 1,595, sorry, 92.5 joules. Okay, and that's the amount of work done on pulling ground. What is the potential energy in the stretched rope? Well, the potential energy in the stretched rope would be your total work, isn't it? So, did we actually get the work done in the initial meter? The original meter we did. We didn't, did we? So here's what we have to do. We never factored in the work from 0 to 1, the initial meter. And then that would be 392 x squared from 1 to 0. And that would be 392 joules. So that's 392 joules to do the original 1 meter extension. 1,592.5 joules to do the extension from 1 to 2.25. Add them up together, and we should get a value of 1,984.5 joules. All right, 5 minutes to get this finished. Okay, a body of mass M rests on a point O on a smooth horizontal surface. It is acted upon by a force in newtons. So basically, My particle, which I'm depicting by a circle, gets pushed, and it's getting pushed with a force F, which is equal to this here. It starts off at point O, and X is the displacement from its original position. If it ends up here, that'll be a distance, X. Is that all right? Now, show that the force dwindles to 0 over 100 meters. No hassle. That's easy. F equals 2 minus x over 50. F equals 2 minus 100 over 50. Equals 2, take away 2. F must be 0. The further you push it, the weaker the force. What happens if I go above 100? The force will end up reversing direction and pushing me back. Is that right? Now, find the work done in moving the force from 0 to 100. All right, no hassle. This is as easy as you think it is. What do you reckon the limits are? 0, 100. What do you think the formula is? Dx, isn't it? Integrate it. What do we get? 2x, yeah. Minus x squared. Divide by the new power. An extra 2, which would be x squared over 100. And then, long and behold, just putting 100 and 0 in. It's going to be 2 times 100 minus 100 squared, take away 100. And your answer is simply 100 joules. And that is question 10 on that exercise, which is really easy. Done. Okay, guys.